So hello there and welcome to another tutorial. My name is Tanmay Bakshi and today we're going to be talking about the transformer architecture and particularly how you can use it for natural language understanding and processing. Now the transformer architecture is really interesting, but before I get deeper into it, I would like to say that if you enjoy this kind of content and you want to see more of it, please do make sure to subscribe to the channel as it really does help out a lot, and turn on notifications so you know when I release videos just like this one today. And of course, if you enjoy the video, please do make sure to leave a like as well. Apart from that, if you have any questions, suggestions, or feedback, feel free to leave it down in the comment section below. I'd absolutely love to hear from you. Now, diving right into the transformer architecture, why is it and why is it important? Well, natural language processing is one of the, biggest fields within machine learning today. And I mean, it's understandable why. It enables such more natural sort of interfaces with technology. But natural language processing is inherently difficult because natural language is a very human mode of communication. It can require creativity to even understand what a certain sentence means, for example. Now, traditionally, the way to understand natural language sentences has been to use, for example, n-gram methods like bags of words, or maybe recurrent neural networks like LSTMs. In particular, recurrent neural networks work by treating natural language like a time series. Take, for example, the sentence, Tanmay likes to record YouTube videos. You could think of this sentence as a series of words over time. Every word modifies the meaning of all the words that came before it and will come after it. And so, by effectively teaching a neural network to look at one word and then create a representation, and then further contextualize that representation with the next word's representation, and so on and so forth, you can create a neural network that can understand natural language in a way. And then you can train it for all different kinds of tasks, like sentiment classification, or maybe you want to train it for regular kinds of classification, like topic classification, maybe regression, all kinds of different things. But there's a couple of issues with recurrent neural network-based techniques. One of them is speed. So take a look once again at the sentence, Tanmay likes to record YouTube videos. In order to generate an embedding for the word likes, which comes after the word Tanmay, you have to have processed the word Tanmay. To come up with an embedding for the word to, you have to have processed the word likes, which requires processing the word Tanmay. And if you get to the very end of the sentence, in order to calculate its representation, you have to have calculated the representations of every single word before it. That's incredibly inefficient because that means for every single token, they have to rely on the tokens that come before them. You simply cannot parallelize that computation. And so you have very inefficient use of accelerators like GPUs or TPUs. Another issue is, well, contextualization. Imagine if your brain could only comprehend the meaning of a word according to the words that came before it, but not the ones that will come after it. That's incredibly limiting. Like, for example, the word YouTube can mean something different based on whether you're talking about the organization, whether you're talking about YouTube videos. The word videos can modify the word YouTube in this specific instance. The word likes can modify Tanmay. How are we talking about Tanmay? What's that context? And to solve this issue, researchers have almost slapped on sort of a technique to try and fix this issue, which is you take the sequence and you just reverse the sequence, and you feed both of those into the same neural network, right? Or rather, two separate versions of the same neural network. So you have, your forward neural network, your backward neural network, and then you take the outputs of the backward neural network, reverse them again, and then you sort of merge the forward and the backward neural nets. But that's not really a solution, because then you can only either look forward at once or backward at once, and then you can kind of try and combine the embeddings. Again, it's really limited. And that's why the transformer architecture was invented by Google researchers. The transformer architecture helps to solve a lot of these issues. And the way that it solves these issues is by making it so that every single token in your sequence can actually communicate and merge with every other token in that sequence at the exact same time. And the best part is that you can do it with a couple of simple matrix multiplications. And that makes it way faster than recurrent neural networks and lets you use accelerators like TPUs or Apple's neural engine really, really effectively. Now, the way the transformer works is actually really elegant, although there are a couple of issues like n-squared memory usage, but we'll get to that in a second. Now, first of all, the idea behind the transformer architecture is that, let's just say, once again, you have a series of tokens, like Tanmay likes to record YouTube videos. Every single token starts off as an embedding, right? So just like with LSTMs, every single word will start off with its own word embedding. after you embed these words into that sort of semantic space, then each individual embedding gets 3 different representations of its own, right? So there's effectively 3, I guess you could call them dense layers in Keras, or linear layers in PyTorch. So you take each token from the sequence and feed it into 3 different multi-layer, or rather single-layer perceptrons. And then what you do is you label those 3 representations the query, key, and value representations, right? So now for your entire sequence, you've got the sequence query representation, sequence key representation, and the sequence value representation. So now what you're going to want to do is you're going to want to somehow merge what all these different tokens actually mean. The way you're going to do that is by using the queries, the keys, and the values. In particular, the query vector can be thought of as almost what other words a certain word wants to merge with. The key is how words want to represent themselves to other words that want to do a merge, and the value is what actually gets merged into that word's representation. So, if you take every single word, and for every word, you calculate sort of like a dot product similarity from that word's query to every other word's key vector. And if you go ahead and get a weighted average of the value vectors for every single word and sum them up according to those dot product similarities, you can go ahead and get a new representation for every single word. Effectively, what you've just done is you've taken individual words and you've come up with new representations for them that actually combine a certain amount of the value representations from every other word depending on the dot product similarity of that word's query and those other words' key vectors. Now, I know this can be a little bit confusing. What you're seeing right now on screen is a diagram of how the transformer actually works. However, I will say, once you take a look at the implementation, it's actually really, really elegant. Now, once you have these new contextualized representations, all you can do is feed them into one more dense layer just to get a better representation, make it a nonlinear transformation. And then, once you've done that, there we go. You've gotten your new embeddings. And of course, you can go ahead and stack more and more transformer layers on top of one another and get a really deep representation of the text that you're trying to understand. Now, here's what's really nice about transformers, or really, before I get to that, a limitation of transformers. One of the main limitations is that, well, in order to get them to be that contextualized, in order to get them to understand language very well and not just attend to very specific parts of a sentence, you actually have to use multiple transformers at each layer that you use, right? So the sort of core component that I've described here, the query key value concept, that's called the self-attention layer. And most transformer blocks will have multiple self-attention heads. And so these query key value representations, let's just say you'll have 8 separate representations like this. You'll calculate 8 separate self-attention sort of new embeddings for all of your tokens, and then you'll feed them into one extra dense layer to merge them all into a single finalized representation. This makes it so that the neural network doesn't need to sort of only focus on certain parts of the sentence, because like imagine if you're feeding a 512 length token sequence into the neural network. If you're running softmax on that, then there's a very good chance you're going to have a lot of very little contribution from a lot of the tokens, or you'll have like one token that has a lot of contribution. So by doing this, you have a neural network that can learn to attend to all different kinds of parts of a sequence. One more limitation is that inherently transformers have no bias in terms of, for example, the position of different tokens within a sequence. And so what's really important to do is before you actually go ahead and run these transformer layers, you have to add extra embeddings to your word embeddings. These are called position embeddings that can either be learned or hard-coded by you. And these position embeddings tell the transformer that, hey, not only is this a token that means this in the semantic space, but also it's located at this specific point within the entire sequence. And of course, there are other kinds of embeddings you can pass in, like segment embeddings and all other kinds of things, but we won't be getting into that for now. Specifically today, we're going to be training what I call a programming language classifier. So a super simple neural network that uses a bunch of self-attention layers. It's built in Keras, and what it does is it takes 4 lines of any snippet of code and predicts the programming language out of 8 programming languages that it was written in. And what this enables me to do is basically take any file of code, split it up into sort of like a sliding window of 4 lines of code, and then feed each of the windows into the neural network to predict what the language is, and then merge those sort of predictions to figure out what language a file of code was written in. This is pretty similar to a natural language understanding task, and we're going to be using a transformer in order to implement it. Now, the only one last tiny limitation of transformers is that their memory usage scales exponentially. And so what that means is, if you were to have, say 32 tokens in your sequence versus 64 tokens in your sequence, you're going to have to store a matrix in memory of size 32 squared versus 64 squared to calculate those dot product similarities. There are some sort of workarounds for this, like for example, Microsoft, Facebook, they've got different models like the Performer, which is a version of the transformer that doesn't have that limitation. But transformers are still absolutely incredible. They've ushered in this whole sort of new era in natural language processing. They reach state of the art in pretty much every task you can imagine. We're even applying them to vision now with vision transformers. It's pretty incredible stuff. And so now, without any further ado, let's take a look at how you can implement transformers from scratch in Keras to do programming language classification. Alright, so now let's take a look at the code behind this transformer implementation. As I mentioned today, we're going to be implementing a transformer that can classify between different programming languages. So for example, if you were to feed in some Python code, then it should be able to tell you that what you fed in was Python code. We're going to do this using the TensorFlow library. It's actually really convenient to implement transformers with TensorFlow. I'll show you how you can do that using the TensorFlow Keras API. And of course, we're doing this in Google Colab, and we're going to be using TPU acceleration. So if you'd like to train your own version of this model, feel free to head over to Colab, spin up a TPU instance, and within a couple of minutes, you should have your own model that should reach approximately the same performance that I have. Now, as you can see, I've gone ahead and gotten a little bit of a head start. I've already connected to my instance, and I've unzipped my data zip here. Effectively, this is just loading in 3 NumPy files. One of them is X, which is our input, including the sort of tokenized individual sets of 4 lines from the different code files. Y is the file containing the labels. So, for example, which examples from the x.npy file correspond to which programming languages. And M is just a mask file. Since I've padded every sample to length 150, mask tells me how many tokens are actually part of the final classification that we want to make, or the input that we're providing for that classification. Now, if we go ahead and get started here, to begin, we can just start off by importing OS, as well as NumPy and TensorFlow, and I'll show you why these imports are necessary in a moment. As a matter of fact, you can see why TensorFlow is important right over here. We start off with a class, specifically a layer, that we are creating a subclass of, called positional embedding. Now, positional embedding is a layer that is necessary with transformers because think about it. If we go back to my explanation of the self-attention layer and how that works, you start to realize that, for example, no matter where the word YouTube appears, or the word Tanmay Bakshi appears in a sentence, or the name rather, no matter where it appears in a sentence, the representation for that word is going to be the same to the transformer. And within the transformer's self-attention layers, there is no inherent bias towards the position of an element, sort of where it is in the actual sequence. So according to the math that the self-attention layer is doing, there's no way for it to take into account the position of individual tokens when it is attempting to make a prediction. Now that can be really bad because, think about it. If I were to give you a sentence like, again, Tanmay likes recording YouTube videos, if I were to not give you the sentence, but rather just give you a set of unique words and how many times they appear in a sentence, that's not really as useful for you, right? Where those words appear within the sentence, in relation to each other is really, really important information. So in order to help the self-attention layers include that information, we effectively calculate a constant embedding that's added to each time step. This is the same embedding for every single sample that we feed into the neural network, just each time step has its own unique embedding that's added to it, such that when the self-attention layers are doing their work, it's possible for them to mathematically separate words from, say, the beginning and the end of the sentence. So what this positional embedding layer does is actually kind of two things. First of all, it does calculate these position embeddings, and it does add those position embeddings to the inputs that you feed in. However, it does do one more thing, and that is it also adds a class embedding. Because think about it, what the transformer does is it transforms token representations to more token representations. So every token now has a new representation. However, when you really sort of dig into what the transformer is doing, you start to realize that, well, how exactly do you take those final new representations and use them to make a prediction, right? How do you take variable length, brand new token representations out of the transformer and convert them to a prediction like, hey, this is written in Python? You could do a couple of things. You could average these embeddings of the tokens, and you could feed them into a dense layer. But another way of doing it is by having a dedicated token called a class token at the beginning of every single sequence, and then using the class token's representation at the very end to make your prediction, and effectively discarding the new representations for every other token at the end. This makes it so that the transformer learns to attend all the discriminative information for the sequence into the class token while keeping the other tokens for understanding the sentence itself. So what the positional embedding layer does all in all is it calculates a class embedding as well as position embeddings for each time step. And then when you call it on certain inputs, it'll go ahead and add that position embedding to the beginning of every sequence. And then it'll go ahead and sum those with the actual position embeddings, making it so that, well, you can add class and positional embeddings more easily. Then after that, I have the actual transformer encoder block. Now, the self-attention part that I was describing earlier, which is the whole self-attention layer, right? And so with queries, keys, and value vectors, that's only a part of the entire transformer. Specifically, it's a part of the transformer encoder block, which includes a few other steps like input normalization, skip connections, attention heads, and more. Now, the encoder block itself is another part of the larger transformer architecture, including the encoder and decoder blocks. Generally, if you want to generate language and do things like translation, then you would use encoders and decoders or just decoders. But if you want to understand language, then you generally just use encoder blocks. Specifically, this encoder block that I'm defining here only takes in 3 parameters. It takes in the parameter ffdim, which is sort of the dimensionality of the final feed forward layer before we give you the new representations. The number of attention heads that we have, so effectively how many individual self-attention layers do we split up into and then merge back in to create new representations. And then first token only. Effectively what this does is it makes it so that the encoder block can return just the representation of the first token, which we know is the class embedding. This makes it really easy to feed the output of the encoder block directly into, for example, a dense layer. Now, outside of the initializer, I then have my build function, and of course in TensorFlow, this is where I go ahead and define all my weights. So let's take a look at how I do that. I start off by figuring out what the size of my input is, and then based off of that information, I create my normalization layer. This normalization layer basically helps us standardize the data distribution for the input coming into the transformer to make the learning process more stable. If you'd like to learn more about how and why that works, feel free to take a look at my video on batch normalization, although I will say this isn't the exact same thing, it is very similar in concept. Now from there, I go ahead and create my attention weights and biases. I do this by creating 3 sets of weights and biases for the query, key, and value. Each one is actually an array, because remember, we have multiple attention heads, and so multiple attention heads call for multiple individual query, key, and value layers. And therefore, I go ahead and use this loop over here for x in range self.heads to create multiple individual weights for the query, key, and value. Now, of course, since we have multiple self-attention layers, but we only want one individual output, we need another dense layer, and this dense layer is represented by, again, a weight and a bias, that is responsible for taking, effectively just concatenating the result of all the attention heads, and calculating effectively a new representation based off of all of their individual representations. The way we do this is by defining a weight with size input size times heads, because of course that's how many individual scalar values we have, that then outputs to a vector of just input size. So we've effectively brought the size back to what it should be. Then we have another normalization layer to normalize the output coming from the attention itself. And then we have the two feed-forward layers that just take our input, generally upscale it to the feed-forward dimension, and then bring it back down to its original size. This helps us effectively have better representations and learn some more mappings that are nonlinear after the self-attention layer itself. When this input is called, or rather when this layer is called with inputs, I go ahead and take the input and split it into the actual tokens as well as the mask telling us where the padding within those inputs are. I go ahead and run my normalization step, of course, to make sure our data distributions are standardized. And then I go ahead and calculate the outputs for each attention head. We do this by calculating the query, key, and value representations for every single input. And then once I do that, I go ahead and calculate the attention scores using that two-dimensional matrix I was talking about before by matrix multiplying the query and the key activations. Once I go ahead and do that, I go ahead and zero out the attention scores for anything that the mask says shouldn't be included in the final result, and then I run a softmax on the attention scores to bring them to a 0 to 1 scale and so that they sum to 1. I then use these attention scores in order to weigh the value activations and append that to head outputs. I then concatenate all the head outputs along their last axis and then use that information to merge all of the head outputs into a single attention output. That attention output we then apply a skip connection to, so effectively we sum in the original inputs from up here. And what this does is it effectively makes gradients flow more smoothly through the neural net. This makes it so that our learning process, once again, is more stable. I then normalize the output of the attention layer, feed it into the first feed-forward network, which generally increases dimensionality, and then feed it into the second one to reduce it back to what it was originally. And then we have another skip connection, adding back in the original attention output even before normalization. And then, of course, if we're only returning the first token, I go ahead and return just that first token from the feed-forward output. Otherwise, we go ahead and return all of it to feed into the next transformer layer. Now, once we've got that layer defined, of course, it's time to build the model. Now, in this case, as I mentioned, I only have inputs of size 150 at maximum. And so I have two inputs to the model, one called input IDs, which is of size 150, and then one called input masks of size 151, because remember, we are adding the class embedding to the very beginning inside of the model, and therefore the masks need to have another sort of index for that padding at the very beginning to make sure we don't just mask out the class variable. Now, once I go ahead and define these two input layers, I can go ahead and embed my input because, once again, the raw input that I'm feeding to this model is quite simple, actually. It's just the index of each individual token in the vocabulary. It's not an actual embedding. So I use a very simple Keras embedding layer in order to embed this into a space of size 256 dimensions. And of course, my vocabulary size is 100, and I go ahead and add a positional embedding to the token embedding that Keras adds for me. Then I can go ahead and call my encoder block a bunch of times. For each one, I'm giving it an internal dimensionality of 512, and I'm telling it to use 2 attention heads per layer. Each time, each block is getting the output of the previous block, except for the first one, getting the output of the embedding layer. I only keep the actual token representations and not the attention scores, since I don't need them in this case. Then I can go ahead and feed the final prediction into a dense layer to predict which programming language was fed into the model. Now, here's what's really interesting about this. We can directly take, once again, that class token output from the last layer and feed that into the dense layer. We don't need extra transformations, although you might want them in some specific circumstances. However, I've found that in this case, it is unnecessary to have additional transformations. There's already enough nonlinearity within the previous transformer encoder blocks. Then I can just go ahead and create a model with my 2 inputs and 1 output, and then compile it with a sparse categorical cross-entropy loss, so I don't need to one-hot my prediction labels. And I can go ahead and give it an atom optimizer with a learning rate of 1e-4, which is a generally good starting point for the atom optimizer. Of course, you might want this to be faster or slower, depending on your specific use case, and in this case, accuracy is a good metric for me. Now, once I've built the model, this bit of code over here just deals with me being in Colab, so needing to connect to a TPU. And then once I've connected to the TPU, I can go ahead and build my model within that TPU strategy scope. I can load in all of my data using NumPy. I can split it into training and testing data sets. And once again, I do need to add a little bit of logic here just to make sure that that the lengths of each individual data array is divisible by the batch size, which in this case is 1024. Otherwise, the TPU doesn't take too kindly to data if it's not divisible by the batch size in terms of how much data you have. Specifically because I am hard coding the model to support specific batch sizes. Then, once that's done, I can simply feed my data, including my X and M and Y arrays, into the model fit function, and then I can go ahead and pass it my batch size, 1024, train it for 10 epochs on the validation data that I fed in. So let's go ahead and run all these cells and see if we get a working model. So I'm going to go ahead and create my layers, define my build model function, connect to the TPU, and once the TPU is done connecting, go ahead and build my model within the strategy scope. I'm going to go ahead and load in my data and print out how much data I have, as well as go ahead and split that data into both a training and a testing split. Once this is all done, we should be good to go ahead and build a model. Train it, rather. And as you can see over here, with the model itself, when you take a look at a summary, has around 3 million parameters. Which for a transformer model is actually pretty small. You can easily get into the hundreds of millions. OpenAI has trained a 175 billion parameter model, so these can easily get much larger. As a matter of fact, for this task, you probably don't even need 3 million. You could probably even get away with half of that, because it is a pretty simple task. However, in this case, I found it's easiest to get good performance with a model of this size without needing much hyperparameter tuning and other kinds of optimizations. But if I go ahead and run a model.fit, it should start training on the TPU. Each epoch should take less than a minute easily, because we're not also training with that much data, only about 400,000 samples. And there we go, training is underway. So, instead of having you watch paint dry here, I'm going to go ahead and speed this clip up so you can take a look at the training process, and then I'll be right back, and we'll take a look at what the results were. Alright, so as you can see over here, the model fit is actually done. We've gone through 10 epochs. Each one took about 24-25 seconds, except for the first one, since that's the first pass where, TensorFlow is doing its XLA optimizations and all kinds of things to get your model to run fast in the future. So you do have a bit of initial overhead. As you can see, our loss, both training and validation, has been going down consistently, and we haven't even completely plateaued yet. I'm pretty sure we could keep this going for a couple more epochs and squeeze out some more accuracy. As a matter of fact, for this architecture and this task, the peak performance I've seen is about 93% on this task. However, in this specific instance, we've gotten an accuracy of 86.7% on the training set, as well as a validation accuracy of 85.99%. And that is how you can train transformer models from scratch in Keras. This task over here enables you to essentially predict the language that a certain piece of code was written in. And of course, I was happy to show you how to actually implement this effectively from scratch, right? Implementing the actual encoder block and the self-attention, because when you do that, you sort of gain a better intuition for how these things work, and it starts to make a lot more sense as to what architectures you should use for what tasks, and why exactly they're used the way that they are. So thank you very much for joining in today. I really do hope you enjoyed. If you did, please do make sure to subscribe to the channel. It really does help out a lot, and turn on notifications if you'd like to be notified whenever I release new content. Of course, if you did enjoy the video, please do make sure to like as well. Once again, really does help out. Apart from that, if you have any questions, suggestions, or feedback, feel free to leave it down in the comment section below, and I'd absolutely love to get in touch. Once again, thank you everybody, and goodbye.